Numerical integration. The problem we want to address here is how to approximate a definite integral using only n plus 1 function values at equally spaced points in the interval. Of course, we can think in terms of approximating the area under the graph of a non-negative function between x equals a and x equals b, although what we will do will apply just as well to functions that aren't necessarily non-negative. Let's begin by describing the points in the interval where we'll evaluate the function. Let xi equal a plus I times delta x for I equal to 0, 1, 2, and so on up to n, where delta x is b minus a divided by n. We can think of these numbers as endpoints of n subintervals, each having width delta x. Note that x0 is equal to a and xn is equal to b, and each xi corresponds to a point on the graph of f with y-coordinate f of xi. We have already seen three ways of using a finite number of function values to approximate an integral. When we first defined the definite integral, we talked about rectangle approximations, in particular, a left endpoint approximation where we sum from I equals 0 to n minus 1 f of xi times delta x, a right endpoint approximation where we sum from I equals 1 to n f of xi times delta x, and a midpoint approximation where we sum from I equals 0 to n minus 1 f of the midpoint between xi and xi plus 1 times delta x. The left and right endpoint approximations are very crude in the sense that typically n must be very large in order to get a reasonably accurate approximation. Turns out that the midpoint approximation does a much better job, but it has the disadvantage of not fitting into our scheme of using a given set of function values at x0 through xn. The trapezoid rule. Consider a typical subinterval from xi to xi plus 1. We want to approximate the area under the graph over that interval using only function values f of xi and f of xi plus 1. A sensible thing to do is to use the area under the segment joining the points on the curve corresponding to xi and xi plus 1. That is the area of the trapezoid shaded in blue here. The area of that trapezoid is easy to write down. A simple way to think of it is that it's the average height times width. So we have f of xi plus f of xi plus 1 divided by 2 times the width delta x. This is the two-point trapezoid rule, which amounts to integrating the linear interpolator between xi and xi plus 1. Now, to approximate the integral from a to b, we just sum up these trapezoid areas as I goes from 0 to n minus 1. Let's call the result t sub n for trapezoid rule with n subintervals, and that will provide an approximation to the integral from a to b of f of x dx. Now let's see if there's a simpler form for this sum. After we factor out delta x over 2, the I equals 0 term is f of x0 plus f of x1, and recall that x0 is a. The I equals 1 term is f of x1 plus f of x2. The I equals 2 term is f of x2 plus f of x3, and so on, until the n plus first term is f of xn minus 1 plus f of xn, and xn is b. So notice that every function value except f of a and f of b appears twice in the sum. So we can rewrite this as delta x over 2 times f of a plus 2 times f of x1 plus 2 times f of x2 and so on up to 2 times f of xn minus 1 plus 1 times f of b. Using summation notation, we can write this as delta x over 2 times f of a plus 2 times the sum from I equals 1 to n minus 1 of f of xi plus f of b. Now let's look at an example. Let's compute t5 for the integral from 0 to 1 of the square root of 1 plus x cubed dx. Since n equals 5, we first compute delta x equal to 1 minus 0 divided by 5, or 1/5, which is 0.2. So our function values will be computed at 0, 0.2, 0.4, 0.6, 0.8, and 1. So t5 equals 1/5 divided by 2 times the function value at 0 plus 2 times the function value at each of the numbers 0.2, 0.4, 0.6, and 0.8, and finally plus 1 times the value at 1. Now with the help of a calculator, we'll compute those function values, and the value of t5 ends up being 1.115. Now it would be very nice to have some idea how accurate this approximation of the integral is. Fortunately, it is possible to estimate the error, and this is what we'll discuss next. Error estimate for the trapezoid rule. A theorem whose proof we will not give because it requires more calculus than we've learned up to now states that if f is continuous on the closed interval ab, and if f double prime of x exists for all x in the open interval ab, then the integral from a to b of f of x dx is equal to the trapezoid rule approximation capital T sub n plus a remainder term of the form minus 1 over 12n squared times b minus a cubed times f double prime of c for some number c between a and b. Therefore, if the absolute value of f double prime of x is less than or equal to some number capital M for all x between a and b, then the absolute value of the difference between the integral and the trapezoid rule approximation, that is, the absolute value of the error, is less than or equal to 1 over 12n squared times b minus a cubed times the number m. So we can compute an estimate for the absolute value of the error, provided that we can find such a number m. Now, for example, for the integral from 0 to 1 of the square root of 1 plus x cubed dx, we just computed t5 equal to 1.115. Now let's estimate the error. We'll omit the details of the computation, but the second derivative of the square root of 1 plus x cubed ends up being 3x times 4 plus x cubed divided by 4 times the 3/2 power of 1 plus x cubed. Now we're interested in the absolute value of this function, and we'd like to estimate the maximum value of this over the interval 0 to 1. Now with the help of a graphing calculator, we can easily plot the graph of that function on the interval 0 to 1. We don't necessarily need the exact maximum here. A fairly close upper estimate will do, and the graph makes it clear that the maximum value on that interval is a little less than 1.5. So a perfectly good value of m here is 1.5. So now we can compute our estimate for the error. The absolute value of the error is now going to be less than or equal to 1 over 12 times n squared, n is 5, times b minus a cubed, that's 1 minus 0 cubed, times our m, 1.5. This number is exactly 0.005. So T5, which is 1.115, is guaranteed to be within 0.005 of the exact value of the integral. Another example. Find n so that t sub n is guaranteed to approximate the integral from 0 to 1 of the square root of 1 plus x cubed dx to within 0.0005, or 5 times 10 to the minus 4. Recall that in the last example, we determined that t5 was accurate to within 0.005, so we want to find out how much bigger n needs to be than 5 in order for the error estimate to be 1/10 as big. Also, from the last example, we know that the absolute value of the second derivative is less than or equal to 1.5 for all x between 0 and 1. So the trapezoid rule error estimate tells us that the absolute value of the error is going to be less than or equal to 1 over 12n squared times the width of the interval cubed times 1.5, which is equal to 1 over 8n squared. Therefore, the absolute value of the error will be less than or equal to 5 times 10 to the minus 4 if 1 over 8n squared is less than or equal to 5 times 10 to the minus 4. So now we just need to solve that inequality for n. Let's multiply both sides by n squared and also by 2,000, and we have 2,000 divided by 8 less than or equal to n squared, which is equivalent to n squared greater than or equal to 250. Now take the square root of both sides. We have n greater than or equal to the square root of 250, which is about 15.8. So now we want to take n to be the next integer greater than or equal to 15.8, and that's 16. So by increasing n from 5 to 16, our error estimate decreases from 5 times 10 to the minus 3 to 5 times 10 to the minus 4. We can think of this as gaining one more decimal place of accuracy in the approximation of the integral by a little more than tripling n. What's happening here is all about the factor 1 over n squared in the error estimate. When we increase n by a factor of the square root of 10, a little more than tripling it, the effect is to divide the error estimate by 10. Simpson's rule. Let's see what happens if we take subintervals 2 at a time, or points 3 at a time. Just as 2 points determine a line, 3 points determine a parabola, assuming the points aren't collinear. Simpson's rule approximates the area under the curve with the area under the parabola. That is, Simpson's rule integrates the quadratic interpolator, whose equation we can write as y equals a times x minus xi squared plus b times x minus xi plus c, where it turns out that a, b, and c are as follows. A is equal to f of xi minus 1 minus 2 times f of xi plus f of xi plus 1, all divided by 2 times the square of delta x. B turns out to be f of xi plus 1 minus f of xi minus 1 divided by 2 times delta x, and c is just the value of the function at xi. These are the coefficients that guarantee that the value of y is f of xi minus 1 when x equals xi minus 1, f of xi when x equals xi, and f of xi plus 1 when x equals xi plus 1, as is not difficult to check. Now let's integrate this from xi minus 1 to xi plus 1. To simplify, we'll make the substitution u equals x minus xi, for which du equals dx, and the limits of integration become minus delta x to delta x, since xi plus 1 minus xi equals delta x, and xi minus 1 minus xi equals minus delta x. The au squared term now gives us 1/3 of au cubed evaluated from minus delta x to delta x, which equals 1/3 times a times delta x cubed minus minus delta x cubed. The bu term gives us 1/2 b times u squared evaluated from minus delta x to delta x, which gives us 1/2 of b times delta x squared minus minus delta x squared. The c term gives us c times u evaluated from minus delta x to delta x, which is just c times delta x minus minus delta x. Now notice that the b term here is equal to 0, the a term is equal to 2/3 a times delta x cubed, and the c term is equal to 2 times c times delta x. Now let's put into this expression our values for a and c. When a is multiplied by 2/3 and delta x cubed, 2's cancel and delta x squared cancels, and we're left with delta x over 3 times the numerator, f of xi minus 1 minus 2 f of xi plus f of xi plus 1. And c is simply f of xi, so we have 2 times f of xi times delta x. Now notice that we can factor delta x from everything. Also notice that we have a minus 2/3 f of xi plus 2 f of xi, which ends up being 4/3 of f of xi, so we can express this entire quantity as delta x over 3 times f of xi minus 1 plus 4 times f of xi plus f of xi plus 1. So we have what we can call the 3-point Simpson rule. Now we'd like to turn this into a so-called composite Simpson's rule by summing up the 3-point Simpson rule over pairs of subintervals across our interval. When I is equal to 1, that formula corresponds to the first 2 subintervals in our interval, and the formula gives us delta x over 3 times f of x0, or f of a, plus 4 times f of x1 plus f of x2. Then we move over to the next pair of subintervals, and for that we need to use I equals 3 in our formula. That gives us delta x over 3 times f of x2 plus 4 times f of x3 plus f of x4. Then we shift over to the next pair of subintervals and we pick up an f of x4 plus 4 times f of x5 plus f of x6, and so on. Notice that with the exception of f of a and f of b, all of the terms here which look like f of xi where I is even appear twice in the sum. So we can rewrite this as delta x over 3 times f of a plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4, and so forth until we get to 4 times f of x n minus 1 plus f of b. So what we have here is a coefficient pattern that looks like 1, 4, 2, 4, 2, 4, repeating until we get to 2, 4, 1 at the other end. Now let's name this approximation S sub n and express it using summation notation as follows. Delta x over 3 times f of a plus the sum from I equals 1 to n minus 1 of c sub I times f of xi and then plus f of b, where the coefficient c sub I is 4 if I is odd and 2 if I is even. Now a simple formula for c sub I would be a handy thing to have. It turns out that we can write this as c sub I equals 3 minus 1 to the ith power. Notice if I is odd, this is 3 minus 1 or 4, and when I is even, is 3 minus 1 equals 2. Now another thing that needs to be emphasized here is that since the rule is constructed by taking consecutive pairs of subintervals, we must have an even number of subintervals. In other words, n must be even here in order for our coefficient pattern to work out correctly. Now let's look at an example. Let's compute S4 for the integral from 1 to 3 of 1 over 1 plus the natural log of x dx. Since n is equal to 4, we'll first compute delta x equal to 3 minus 1 divided by 4, or 1/2. So our function evaluations will take place at 1, 1.5, 2, 2.5, and 3. Now S4 will be 1/2, that's delta x, divided by 3 times f of the left endpoint 1 plus 4 times f of 1.5 plus 2 times f of 2 plus 4 times f of 2.5 plus 1 times f of 3. Now f of x is 1 over 1 plus natural log of x, so this turns into 1/6 times 1 over 1 plus the natural log of 1 plus 4 times 1 over 1 plus the natural log of 1.5, plus 2 times 1 over 1 plus the natural log of 2, and so forth. Now with the calculator, we'll compute each of those terms, and then finish up the computation. We end up with 1.26519. Now, just as with the trapezoidal rule, it's very desirable here to have some idea of how accurate this approximation is, and that's what we'll look into next. Error estimate for Simpson's rule. This is going to be similar in spirit to what we saw for the trapezoid rule. If f is continuous on the closed interval ab, and if the fourth derivative of f of x exists for all x in the open interval ab, then the integral from a to b of f of x dx is equal to capital S sub n plus a remainder term of the form minus the fifth power of b minus a divided by 180 times n to the fourth times the fourth derivative of f evaluated at c, where c is some number between a and b. Therefore, if the absolute value of the fourth derivative is less than or equal to some number m for all x between a and b, then the absolute value of the difference between the integral and the Simpson's rule approximation is less than or equal to b minus a to the fifth over 180 times n to the fourth times the number m. Probably the most important thing to notice here is that the estimate on the right-hand side has n to the fourth in the denominator, where the trapezoid rule error estimate had an n squared in the denominator. Now, for example, for the integral from 1 to 3 of 1 over 1 plus log x dx, we computed S4 equal to 1.26519. Now let's compute a bound on the error. Now we'll skip the details again, but after a considerable amount of work, we find that this is the fourth derivative of f, and it's the absolute value of that we're actually interested in. Now again, rather than trying to find the exact maximum value using calculus, we'll just graph the function with a graphing utility, which reveals that this function is actually always decreasing on the interval from 1 to 3. That tells us that the maximum value is the value at the left endpoint, which actually turns out to be exactly 88. So now we're ready to compute the estimate. The absolute value of our error is less than or equal to the width of the interval, which is 2 raised to the fifth power, divided by 180 times the fourth power of n, which is 4, times 88. This turns out to be 0.0611 rounded to 4 decimal places. So we now know that our computed S4 is within 0.0611 of the exact value of the integral. We should point out here that this error estimate is likely to be quite conservative. That's because the absolute value of the fourth derivative that appears in the exact formula for the error is likely to be considerably less than our upper bound of 88. Another example. Let's find n so that s sub n is guaranteed to approximate the integral from 1 to 3 of 1 over 1 plus log x dx to within 5 times 10 to the minus 5. From the previous example, we know that 88 is an upper bound for the absolute value of the fourth derivative of f on the interval from 1 to 3. So, using the formula for the error estimate, we have that the absolute value of the error will be less than or equal to the interval width 2 to the fifth power divided by 180 times n to the fourth times 88. This turns out to be equal to 15.644 divided by n to the fourth. Therefore, the absolute value of the error will be less than or equal to 5 times 10 to the minus 5 if 15.644 divided by n to the fourth is less than or equal to 5 times 10 to the minus 5. So now we just solve this inequality for n. We multiply through by n to the fourth and divide by 5 times 10 to the minus 5, and we get n to the fourth greater than or equal to 312,880, roughly. Now we take the fourth root of both sides, and we obtain n greater than or equal to 23.65. And finally, we choose n to be the first even number greater than or equal to 23.65, which is 24. So we now know that s sub 24 will estimate our integral to within 5 times 10 to the minus 5. Calculators and the trapezoid rule. Let's think about how we might implement this trapezoidal rule formula on a common calculator. One way of approaching this on a TI-83 or 84 calculator is to press the y equals button and then enter the formula as the function y2. Here we're using x as n, and we'll assume that values of a and b have been entered on the home screen. Notice that the formula refers to the function y1, so that's where we'll put the function that we're interested in integrating. So if we want to integrate x cubed, we'll make that y1 of x, and then on the home screen we'll store 0 as a and store 1 as b, and then enter y2 of 10, which will give us the trapezoidal rule approximation using n equals 10 subintervals. Now let's look at how we entered our formula. The sum from I equals 1 to n minus 1 of f of xi is here where we use the sum and sequence functions in the calculator, which are found in the list menu. What sequence does is just create a list of values and then sum adds them up. On a TI-89 or 92 calculator, we can essentially just enter the formula and store it as a function of a, b, and n. Here we're storing it as a function called trapeze, and now to use this we'll need to define the function f. So let's say we store x cubed as f of x, and then we type trapeze of 0, 1, 10 with those commands separated by a colon, and we get the trapezoidal rule approximation to the integral from 0 to 1 of x cubed dx using 10 subintervals. Now let's compare this formula to what we did with the 83 and 84 calculator. Here we use the summation function represented by the capital sigma, which does the work of both the sum and sequence functions on the 83 and 84. Now in both cases there are ways of doing things a little bit better, particularly with the 83 and 84, where it might be nice to write a program that prompts the user to input values of a, b, and n. What we've given here are just simple ways of getting things done that don't require us to think about programming. Calculators and Simpson's rule. So now let's think about this formula. There really isn't much difference from what we just did with the trapezoidal rule. We just need to make a couple of changes. On the 83-84, the function specified using x for n as y2 of x looks like this. Let's highlight the main differences here. Notice the coefficient 3 minus -1 to the ith power inside of the sequence function, multiplying y1 of a plus I delta x, And notice that the 0.5 times b minus a over x, or 0.5 delta x, has been replaced by 1/3 of delta x in the form of b minus a divided by 3 times x. And notice the necessary parentheses around the 3x there. So now if we let y1 of x equal x cubed, back on the home screen again, we'll store 0 as a, 1 as b, and then enter y2 of 4, and this will give us the Simpson's rule approximation using n equals 4 to the integral from 0 to 1 of x cubed. And notice that we get the exact value, 1/4 here. It turns out that Simpson's rule does in fact integrate cubic polynomials exactly. On an 89 or 92, we'll call this function Simpson, SIMPSN, and again let's highlight those same differences in the formula. You have your coefficient of 3 minus -1 to the I, multiplying the function values inside of the summation, and b minus a divided by 3 times n, which is 1/3 of delta x out front. And now if we store x cubed as f of x, and then type Simpson of 0, 1, 4 with those commands separated by a colon, we'll again get the Simpson's rule approximation using 4 subintervals, which again equals 0.25.